Continuing on with our next redistribution, case number 3 here, we see that this is likewise a similar topology to the previous 2 examples, but now we've traded EHRP to OSPF, or excuse me, we traded EHRP to RIP version 2, and then we're doing redistribution one way at multiple points between different points of the topology. Now, again, if we look at the specifics here, the description, it tells us which way the redistribution is happening. It says that routers 1, 2, 3, 5, 8, and 10 are running OSPF area 0. So if we take a look at this on our diagram, we have the same OSPF over here, but the difference is now we're running RIP as opposed to EHRP. So OSPF is getting redistributed into RIP on router 1, and then RIP version 2 is getting redistributed into OSPF on router 3. Now again, as we talked about the general cases with the potential cases for loops, there is either a loop that's based on the distance or there is a loop based on the metric. Okay, assuming again we're not talking about bugs in the process where maybe the route didn't get downloaded to the forwarding table correctly and there's a loop in the data plane, that's not a normal situation. Okay, we're talking about here either a control plane loop or a data plane loop that's caused by just one of these 2 particular parameters. Now here in this case, when we're dealing with RIP version 2, as I mentioned, one of the things that we need to think about is that it cannot tell the difference between internal versus external routes. So when we're redistributing a route from RIP into OSPF, OSPF tags it as external, but when we go from OSPF back into RIP, RIP is just going to see it as a RIP route. There's no field in the update to say that it came from the external domain. So then depending on what the seed metric originally is, we could have either a problem with the metric or we could have a problem with the distance because the distance of OSPF is lower. So again, the key telltale symptom that should be like a red flag here is that when you're going from a high administrative distance to low, and then the route is somehow getting fed back. So here specifically in this case, we're going from high to low, and then it's being received back on router 1, and then router 1 is redistributing it back into the RIP domain. So then let's look at what's the end result from reachability. So we have our TCL script. Let's go ahead and say we're just going to start with sending 10 pings to the different loopbacks. And if this is a permanent loop, which means that someone is deciding the control plane wrong, but yet the decision is stable, normally what this means, again, is that we will have 0 reachability to the destinations. Where again, this is different from the previous case, that if we have partial reachability, that's a little bit more difficult to track down, because then we would have to look at what is specifically churning in the routing table, who is doing the original churn, why are they choosing one route over another, and why are they making the wrong decision. But in this case, when we look at the result of the pings, it's fairly obvious. The devices in the OSPF network don't have reachability to certain portions of the RIP domain, depending on where you look at it from. So router 10 has reachability to everyone except router 9. Router 8 likewise does not have reachability to 9. And then depending on where else we're looking at it from, router 1 has issues with, actually it looks like nobody else right now. But this will depend kind of on the order that the process loads. So again, we need to think about from a visual point of view, how are the routes originated to begin with? So if we start on router 9 and we look at how is this route being advertised, it's being advertised as a RIP route, and it goes up to router 7. If we look at router 9 specifically, and we look at let's get out of the TCL show, and we look at the show run section router, in this case, router 9's link is advertised with a high metric. So it says we're doing connected redistribution, the metric is 6, and then this particular route map is matching a connected interface. If we show route map, matching the loopback here and then setting the metric to be a high value. But what this is basically simulating is not necessarily router 9 redistributing its connected link with a high metric. It means that there's multiple devices behind router 9 that are advertising routes into the RIP domain. And I'm going to show a little bit of a variation here to talk about what are the key behavioral differences between distance vector and link state in terms of advertising routes. And as I mentioned in the previous section, there are some cases that are based on distance that you cannot fix by setting the route tag. So first let's look at the resolution for this, and then we'll look at a couple minor variations to see what exactly I meant by that. What are the situations where tagging will not help you? So as it stands now, router 6 is advertised, or excuse me, router 9 is advertising this update, and it's advertising it with a metric of 6. So it gets to 7 with a hop count of 6. Router 7 continues to advertise it on, and RIP is simply incrementing this on a hop-by-hop basis. So router 6 should say, I have a metric of 7. Router 6 is going to advertise it to router 1. Router 1 says I have a metric of 8. Router 3 now redistributes this route into the OSPF domain. Now in cases where we have, like we do here, router 1 has a route to 3 via OSPF, or a link to 3 via OSPF, and then it also has the RIP domain, we know which one it's going to choose, correct? It's going to choose OSPF because OSPF's distance is lower. So the route gets advertised from 3 to 1. 1 is redistributing it back into the RIP process, and depending on what the seed metric is, we could now cause a loop situation. Where this case is going to be a loop again in the data plane, not necessarily a loop in the control plane, but it's a wrong decision that's made in the control plane. So on router 10, when we do a trace and we look at the trace to the destination we can't reach, this is obvious that there's a problem. That the route is looping over and over and over and over, but it's looping in the data plane as opposed to looping in the control plane. So this is another example here where looking at debug IP routing is not going to help. Looking at the IP route profile is not going to help because the table is stable, but it's stable in the wrong condition. So someone is pointing the route towards the wrong interface. And again, if we look at here in the loop, where specifically did we enter and then not able to exit? That's the device where the problem is. So it says it's going from 8 to 5 to 3 to 7 to 6 to 1 to 3 to 7 to 6. That's where the issue is. So the loop is happening here between 1 and 3. That's where it gets fed back. And this is now where it's infinite. So this basically means router 1 is the device making the wrong decision. Specifically, if we go to 1 and then look at the route to the destination, show IP route 151.99, it says this is installed via OSPF, and then we're redistributing it via RIP. Now, depending on whether we want to do this or not really depends on what's going on in the rest of the topology, because if the only route to router 9 possibly is through 7, it doesn't make sense again to advertise these prefixes. So there's a number of different ways to solve this. We could do it at redistribution by saying don't redistribute 9's prefix back that was originally a RIP route back into RIP. We could say filter it out with the distribute list under the process, just router 1 stopping the advertisement out to router 6. We could filter it in OSPF with the distribute list to stop it from going in the routing table, with the ultimate goal being that we simply want to make sure that the route coming from the high administrative distance protocol going to the low one doesn't get fed back to the high one, because then it's going to be preferred depending on what the ultimate seed metric is. Now in the case of RIP, this becomes a little bit more difficult because the maximum metric value is very low, which is 16. So if you set the metric too high when you seed it into redistribution, like let's say we set it to 10, it means that there's only 5 different hops that you can go through before the route itself becomes infinite. So when I advertise you a route that has a hop count of 15, you can't advertise it on to anybody else. You increment it to 16 and then it becomes infinite. Now we'll see a little bit later when we talk about filtering, this could be a way to forcibly filter a route in RIP. Like from router 1, maybe I want router 6 to go this way to get to the destination. What I could do would be to send the route with a metric of 16 in this direction and then send the route with a metric of 15 in that direction, so that 6 would be able to use it, but it wouldn't be able to actually pass it on to any other destination. But again, the big indication with this type of problem is the output of the trace. That if the trace shows that the loop continually happens in the data plane, then it's unlikely that a debug IP routing or the IP route profile is going to help you. So what are the different ways that we can fix this then? Okay, one of the suggestions was let's just have router 1 seed the metric higher. So the originator was setting it to be 6. Let's say on router 1 we set it to a metric of 10. So when we go to the RIP process, if we look at the show run section RIP, and we're redistributing OSPF in there, let's just say that we add a 0 to the end of this, so we're advertising it with a metric of 10 as opposed to a metric of 1. Okay, eventually once this updates, and it's going to take a minute unless we clear out the table manually, because the RIP update interval is a slow value. So we can see here now the metric is 11 via router 6. And eventually, once router 9 sends its own update, we should see a changeover. So now we can see it was originally a metric of 11, which was the new seed metric that I was setting in. Now it's a metric of 6. End result should be that we're now routing the traffic in the correct direction. But let's talk about what are some other cases where doing filtering would not help. Okay, so let's say we're not going to do the seed metric. That's one of the possible solutions. Let's say that we're doing it by doing a route tag as opposed to doing a filter directly on the route, because that's basically what we're doing here by setting the metric high, saying that I'm going to give you the route, but you can't actually use the advertisement. So let's say that we're going to do this with a tag as opposed to the metric. So let's go back to the OSPF process, or actually the RIP process, and let's revert to what we previously had, which was redistribute OSPF 1 metric 1. Okay, next between router 1 and router 3, let's look at who is actually using routes that are pointing into the RIP domain. Because one of these devices is going to prefer to use OSPF over RIP, correct? Because the issue is what? The issue is the distance of RIP is higher. Now, we could solve this again by redistributing mutually in both directions and making sure that the seed metric is higher, but eventually one of the routers is going to choose the OSPF route, one of them is going to choose the RIP route. Okay, so let's now say that we make the change on both 1 and 3 so that we're redistributing both directions, not just one. And we're going to do just a very basic redistribution. So let's say under router 3, let's say show run section router, which is that one. So we're saying under OSPF 1, redistribute RIP subnets. And then under RIP, we're going to say redistribute OSPF 1 metric 1. Redistribute RIP subnets. And then let's say under RIP, we're going to redistribute OSPF 1. And let's say the metric is a little bit higher. Let's say the metric is 7, which I believe should fix the problem. But we're going to do this on 3 on 1. Then on all the routers, let's go ahead and clear just say clear IP route star. Clear IP route star. So RIP version 2 by default does support triggered updates. If you clear the routing table, it will refresh the route. But if you leave it by default, it's going to take a little bit of time in order for it to send the normal update. Or if there's an old update in there, it takes about, I want to say 3 minutes or so in order for it to flush out of the table. So you may be better off just doing this, say clear IP route star, and that would delete it from the routing table. So let's look at everybody now, and let's just say show IP route everywhere. And let's look for that specific prefix, show IP route 150.199. Okay, router 1 says I'm using OSPF to get there. The originator in the OSPF process is router 3. Router 2 says I'm going to use OSPF. That's its only option. It's only in the OSPF domain. So let's point here on the diagram which way they're routing. Okay, 2 is routing that way. 1 is routing that way. 4 should route towards 5. 5 should route towards 3. Okay, so 3 is the central collection point now for this traffic. And then 8 and 10, this is their only path, so they're going to go to 5. On the RIP side, router 6 says I'm going to go to router 1. So the metric here is still bad. That's not going to be a high enough metric here in order for 6 to fix the problem. Actually, no, we can get there now, but we're just going the wrong direction is what it is. Actually, we're doing load balancing. We're doing ECMP now. So from 6, we're going both ways because it's both a metric of 7. Okay, then router 7 should say I'm going to go directly to 9. Okay, now everyone should have reachability. So let's double check this on all the boxes where we ping 151.99, and let's say we're a peak count of 1,000 packets. Okay, so it looks like everyone was able to fix it. So simply by seeding the metric a little bit higher, but also I did mutual redistribution in this case, from OSPF to RIP and back on router 1, and OSPF to RIP and back on router 3. But notice what happened here. One of the ABRs, or actually one of the ASBRs, so the person doing the redistribution, one of them is preferring to route internally versus one of them routing externally. Specifically here in this case, router 1 is going into OSPF in order to get out to the rest of the RIP network. Now, in this specific case, it's not really an issue, and the reason why is that router 1 is not transit for other destinations in the RIP network. But let's say we make a change here. Let's say that we were to add another router. Let's say that we're going to add router 11 behind router 1 and have this router be part of just the RIP network. Router 11. So let me open up a new window to another box on this segment, router 11. Which is unconfigured. So let's go ahead and add router 11 to this segment. We're going to say that router 11 has an interface gig 1 111 that is VLAN 111 and cap.1q111. IP address will be 155.1.111.11. And that's pretty much it. Okay, we'll say on the main interface, no shutdown. And then under RIP, version 2, network 155.1.0.0. On router 1, then I need to add this additional link. So let's say we have interface gig1.111. Encapsulation is .1q111. IP address is on the same segment. So if we ping 155.1.111.11, we should be able to reach that box. Okay, but the key point here being that this new device is only in the RIP domain, it's not in the OSPF domain. So what does this now mean from a reachability point of view? If we were to predict what is router 11's view of the topology, right now we saw everyone else was able to reach everything. But from router 11's perspective, will it be able to reach OSPF? Will it be able to reach RIP? What do you guys think? Well, it really depends. What are the advertisement rules of the distance vector protocols? In order to advertise the route, what has to be true? And this is the same with both RIP and EIGRP. Then in order to advertise the route, it must be in the RIB. Or in other words, it must be in the routing table. But from router 1's point of view, if we were to look at the show IP route RIP, what's the issue? We don't have any RIP routes because we're preferring to route into the OSPF domain due to the lower administrative distance. And this is one of those situations where using a route tag is not going to help you. Simply based on the default behavior that if you want to advertise the route as distance vector, you have to use the route, means that 11 won't learn anything. And doing any type of filtering on router 1 would only help if we could force it to install the RIP routes into the routing table. So on router 11 here, if we look at the show IP route RIP, the only thing that's going to be advertised here is, well, let's see, one is doing direct redistribution is what the issue is. It would have to be a case where one is not the person doing the redistribution. It would actually have to be on it would be this case. If one did not redistribute the reverse direction, so if we went into RIP and said no redistribute OSPF, now 11 would lose its view with the exception of what router 1 has directly connected. So this is another problem that you have to take into account, and you normally would only see this either with eIGRP or RIP because they're distance vector protocols. That you feed the routes from the eIGRP rib or the RIP rib, which you can see in the case of RIP if you show IP RIP database, or in eIGRP, that's the show IP eIGRP topology. So out of the best routes here, we then decide what goes into the routing table. Those are the ones that we can advertise. Those are the ones that we can redistribute. But in the case of OSPF, it doesn't work like that. As long as you have the route in the database and the routing bit is set, you should be able to advertise it. Now, we will talk about some other corner case situations in OSPF where that might not be the case. It depends if you have an LSA3 and you're trying to re-originate an LSA3 about someone else's origination. It starts to get a little bit more complicated when we look at distance vector inter-area routing. But in general, OSPF will advertise the route regardless whether it's actually in the routing table or not. But eIGRP and RIP never will, which means that now in this type of case, really the order of operations is going to be dependent on what actually happens. So if router 1 chooses to route into the RIP domain, then it can advertise the routes to 11. But if OSPF is used instead, then it's never going to happen. So in this case, even if we were to set a route tag, it's not going to help. What we would need to do instead is to go to router 1 and say something like this. Router OSPF1, set the distance for OSPF for external to 121, which now means that we should be able to install the RIP routes as RIP routes. If we clear IP route star, which then means we can continue to advertise them, and then ultimately we should be able to get reachability. There's a question here. So if router 11 was OSPF and router 1 installs routes for eIGRP, will router 11 be able to reach the eIGRP domain? It's exactly the same case. So you could take this exact same diagram and switch out RIP with eIGRP, and depending on the order that this process loads, if it routes that way into RIP/eIGRP, then the routes would be allowed to be advertised to router 11 via whatever that protocol is. But if OSPF is preferred and we route that direction, we would never do the advertisements because of the distance vector nature. That you simply cannot advertise a route that is not in the RIB because you don't have end-to-end visibility. But again, with OSPF, it's different because we already know the graph of the topology. I've already solved the shortest path to all the nodes in the tree. So even if I'm not using that in the routing table, I can still guarantee it's loop-free when I advertise it to somebody else. So again, the real big takeaway from this is that you cannot put general rules on redistribution other than what are the potential problems being the difference between the metric-based loops and the distance-based loops, where some of them you'll see the result is a data plane loop, some of them you'll see as a control plane loop. But you don't want to put general rules to say when I redistribute I should always use tags, or when I redistribute I should always change the distance to this value, because it depends on how the topology is laid out. In certain cases, a design like this could be solved with tags. In certain cases, it can't. And that's part of the mental exercise here with these redistribution scenarios, and we're going to continue to add more of them, is that you need to get to the point where you can simply look at the diagram, step back and think about it for 5 minutes, trace out the routes, and then ultimately you say, okay, here's the problem it's going to be because router 1 installs OSPF versus RIP, can't advertise RIP to the other neighbors, it's going to withdraw the routes, and then the solution is to change the administrative distance so that the RIP routes get into the routing table and then ultimately can get advertised. But it does take a lot of practice. It's not one of those things that really seems very intuitive simply because there are so many different cases that you would need to cover. but the general logic is always there going to stay the same about the reason that the loop is occurring.